All right, guys. So we talked about formal charges, how to calculate those last time. And now we're going to talk about, I mentioned this at the end of the last video, but how to select the most stable resonance structures if you have more than one resonance structures. Remember, resonance structures are two or more Lewis structures that in general follow the octet rule, right? And everything's good there, or the duet rule for hydrogen, and you have the right number of valence electrons. But in some cases, when you have multiple atoms, you can just have multiple structures that satisfy that. So sometimes more than one resonance structure will be a good reflection of reality. Sometimes one will be a better reflection than the other. And so there's two rules to figure out, which one, if any, is better than the other. And these are the two rules. Structures with formal charges closest to zero are the most stable. Okay. Basically, nature doesn't like charge, right? And the second one is if there are no non-zero charges. So if you have to have charges, formal charges that aren't zero, you better have the negative charges, the negative formal charges on the electronegative atoms, because those are the atoms that want electrons, right? They're more electronegative. And you better have the positive formal charges on the more electropositive atoms, or the less electronegative atoms, right? Because those are the elements that want to give up electrons. The other thing I will say here, just as a note, and we'll go through this when we're working on this next problem, but your formal charges of all the individual elements have to equal the total charge of the ion, or if it's not an ion, it has to equal a neutral it has to equal zero if it's neutral. Okay. All right, so let's go through this problem. Based on formal charges, which multiple ones, or which one is the best structure for nitric acid? So I've already given you the different resonance structures just to save us some time. Of course, you could have come up with this yourself. And so now we're going to go ahead, and for all these different elements, we're going to calculate formal charges. So here's hydrogen. Hydrogen has one valence electron, right? And so remember the formula for formal charges. Again, it's valence electrons minus non-bonding electrons minus bonding electrons divided by 2. That's formal charges equals FC. FC, we'll say, stands for formal charge. Okay, so for hydrogen, that's going to be one valence electron minus, it doesn't have any lone pairs, 0 non-bondings, minus one bond, or bonding electrons divided by 2. So that's going to be equal to 0. Oxygen here. Oxygen 6 valence electrons minus 4 non-bonding, right? There's 2 lone pairs, minus 2 bonds. It's 2. So that equals 0. Nitrogen. Let's draw an arrow here. Nitrogen's 5 valence electrons. 1, 2, 3, 4 bonds, 8 bonding electrons, 8 divided by 4, and no lone pairs, right? So that's going to be plus 1. This oxygen down here, oxygen's group 6, minus 4, 2 lone pairs, non-bonding electrons, minus 2 bonds, that's 0. And this oxygen is, again, 6 valence electrons, 2, 4, 6 non-bonding, and there's 1 bond, so minus 1, that's minus 1. So basically we had a 0, a plus 1 for nitrogen, a minus 1 for this nitrogen, and a 0 for this oxygen. So if you add all those up together, a 0 plus a 0 plus a negative 1 plus a 0 plus a positive 1 equals 0. And that's good because the whole molecule was neutral. Okay, so that's just something I mentioned before we got to the slide at the end of the previous slide. All the formal charges of the individual elements should equal the total charge of the molecule or ion. And in this case, it's a neutral molecule. So we want all the formal charges to be equal to 0. If we don't get that, we did something wrong with one of the formal charges. Okay, keep going. This one. 1 minus 0 non-bonding minus 1, okay, equals 0. Here, oxygen is 6 valence electrons. There's 4 non-bonding, and we have 2 bonds. It's equals 0. Here, nitrogen, that's 5 valence electrons. There's no non-bonding, and there's 4 bonds. So that's going to be +1. Oxygen has 6 valence electrons, and it has 2, 4 non-bonding, and then it has 2 bonds. So that's going to be 0. And oxygen here is going to be 6 valence electrons, 2, 4, 6 non-bonding, and 1 bond. So that's -1. And again, 0 plus 0 plus 0 plus +1 plus -1, that equals 0. We did it right. Down here to hydrogen. Hydrogen has 1 valence electron, no non-bonding, there's no lone pairs, minus the 1 bond, that gets us 0. Oxygen, 6 valence electrons, 2 in the lone pair, and then we have 3 bonds. That's going to be +1. Nitrogen in the center there, 5 valence electrons, 5 minus 0, there's no non-bonding, minus 4 bonds, +1. Oxygen here, 6 minus 6 non-bonding, minus 1 bond, -1. And oxygen here, 6 minus 6 minus 1, -1. Did we do this right? -1 plus -1 is -2. -2 plus 1 plus 1 plus 0 is 0. So yes, we did it right. Now, which one is best? All right. Well, we want ones that have closest to zeros, okay? That was our first rule, closest to zeros. And so here we have 1, 2, 3 zeros. Here we have 1, 2, 3 zeros. Here we only have 1 0. So that tells us right away, you know, it's not going to be this one because, you know, only 1 0 formal charge. Nature doesn't like charges, so we don't want this one compared to the other ones. We have a better option, right? What that means is this is not as good of a reflection of reality. It's not as good of a reflection to have a double bond here. It's better to have a double bond here or here, right? And let's look at here. Are there any differences here? 0, 0, -1, 0, 1. We have a 1 on a nitrogen and a 1 on a nitrogen and a -1 on this oxygen or -1 on this oxygen. Well, those are the same type of oxygens, really. I mean, one I just drew up here and one I drew down here, right? These structures are the same, okay? So basically, the way to think about this is these resonance structures, okay, are both the same, and they're equally valid. They're equally valid reflection of reality, okay? And we could draw a double-headed arrow to show that they're interconverting. But, you know, look at here and here. The only differences are the double bond and the single bond, the location of those, right? And so what it's telling you is, you know, going a little bit deeper with this idea of resonance, basically, it's not a double bond and it's not a single bond there. You have a total of 3 bonds between 2 bonding sites. It's more like a 1.5 bond. Okay, so it's intermediate strength between a single bond and a double bond because it's resonating between both these structures. They're equally valid, and so really you have delocalized bonding across that site. And so that's what that's saying. All right, that's a little more advanced like interpretation of this, but you know, you should be able to figure out all the different resonance structures for Lewis structures for a given molecule, and then be able to tell me, you know, which of those resonance structures is the best approximation of reality based upon the formal charges. Again, close to 0. Here we didn't have to use the fact that more negative more negative formal charges would want to be on more negative electronegative atoms. But actually, if you look at these cases here, right, you have a +1 that's relatively electropositive compared to the -1 on the oxygen, which is relatively electronegative. So that's actually a good situation. So everything's lining up well, And those top two resonance structures are the ones that are better reflections of reality.